When you're training a neural network, it's really important to choose the right features and the right training objective. Take, for example, a music recommendation system. Let's just say you train one based off of the name of an artist and the lyrics of a song. Well, how's your neural network going to tell the difference between vocal frequencies in an original song and in a cover song? Well, it won't, and that's a problem. But suddenly, feed in a Fourier transform of the vocals and change the training objective a little bit, and suddenly you've got a much better recommendation system. Similarly, when it comes to natural language generation, why do we only train neural networks to predict the next word? We're only training greedy next word predictor systems. Well, to figure out why and how we can actually solve that problem, to teach neural networks to write, and to discover more about the world of natural language processing in general, I'd like to invite you to join the 25th episode of Tech Life Skills with Tanmay. We're going live in 30 minutes featuring a very special guest, Allyson Ettinger, an assistant professor at the University of Chicago Department of Linguistics.
That's right. We're going live in 30 minutes. I'm Allyson Ettinger, and we're going to be talking today about natural language processing and other issues of language in machines versus how language works in humans.
When you're training a neural network, it's really important to choose the right features and the right training objective. Take, for example, a music recommendation. Hello everyone, and welcome to the 25th episode of Tech Life Skills with Tanmay. My name is Tanmay Bakshi. Thank you very much for joining today, everybody. And before we get started, I do want to share with everybody some really good news, actually. So just yesterday, my amazing sister, Tanvi, actually got married to the amazing Rohit. So a huge congratulations to them. And right after the show, I do look forward to having a lot more fun with them as well. And I gotta say, by the way, that the wedding cake yesterday was pretty amazing. But I digress. Now, on today's show, we're going to dive deep into the world of natural language processing, and specifically, we're going to be talking about some of the technical challenges that we face, why we face those challenges, and what we are doing to actually overcome those challenges as well. Now, I think personally that this is really important, and the reason that I'm so passionate about natural language and really being able to comprehend natural language and write natural language with the power of technology is because that's the way we humans have evolved to communicate, right? That's how we talk to each other. And why should we have a separate interface of buttons and switches talking to technology, whereas we could be talking to them in natural language as well, right? If we want technology to play an even more integral part in our lives and be able to augment our capabilities further, it makes sense that we should be able to communicate with them just like we communicate with other living humans. And so that's why I'm so passionate about the world of natural language understanding, and I'm very excited because I'm going to be learning a lot on today's show as well, because we're being joined by our very special guest, Allyson Ettinger. She is an assistant professor at the University of Chicago Department of Linguistics, and she has a PhD from the University of Maryland. And so now, without any further ado, I would love to welcome Allyson to the show. Hi, Allyson. How are you?
Hi, I'm doing well. Thanks. How are you doing?
I'm doing very well. It's great to have you on the show. I've been really looking forward to this episode. And as a matter of fact, actually, before we begin, I would love to hear a bit more about sort of your story. How did you get to what you're doing today? Would you maybe like to also quickly introduce yourself for the audience?
Yeah, thanks for having me. Hi, I'm Allyson Ettinger. I am, as Tammy said, an assistant professor in the Department of Linguistics at the University of Chicago. How did I get here? So I started out on this path based on an interest in language, in humans. I got really excited as a kid in learning languages, and not all linguists get interested in linguistics via being interested in learning languages, but that was the case for me. So I liked learning languages. I started studying linguistics as well as psychology in college, and then I worked later on in a neuroimaging lab, which was doing brain imaging as humans are listening to or reading language and seeing how their brains are responding to that and trying to understand things about the mechanisms in the brain. Then I went to do my PhD, and I got really excited early on in my career as a PhD student in trying to engineer machines to be able to handle language the way that the human brain does. And so I got interested in computational linguistics and natural language processing, and I became, at that point, a computational linguist, and that brings us to where we are now.
Very nice. That's so fascinating to hear because, I mean, the reason that I got so interested in language, just to sort of put this into a bit of perspective, it was actually quite similar to, why I actually got into the world of machine learning in general. And I feel like we came at this from different angles. You mentioned that, you got interested in linguistics because you had this fascination for learning lots of different languages, which sort of initially got you into like, how can we understand language? But one thing that actually got me interested in language was a few years ago when I saw the Watson Personality Insights service. And I was like, how is it possible for us to be able to identify personality traits from the way that we structure natural language, right? That just really fascinated me. I was like, there's so much hidden insight that we can extract if we were to somehow like understand that data better, that I was like, you know what, I've got to work on natural language processing in specific, right? So that was what sort of initially hit me as I want to work with natural language. Now, one thing I will say, we are already actually getting a couple of questions from the live stream, so we will be getting into those in just a moment. But I actually want to start off by sort of asking you a little bit more about the world of natural language and why you think it's important for us to do more research into the world of NLP and being able to comprehend natural language. Because if you think about it today, we have pretty good natural language processing technology. I mean, compared to a couple of years ago, it's stellar, right? We've got new technologies like BERT that are helping Google with the search engines. We've got, even before BERT, we already had Apple that was working on, trying to put word embeddings into context across a whole, global sort of span of text, and they were trying to apply that to Siri. And so we've already had all this technology. What do you think makes it so important for us to want to advance further the state of the art in natural language processing? What can we do with that technology?
Yeah, I think these are really important questions, and there are a lot of parts to what you asked. Natural language, as you said, sort of at a basic level, the reason we would want machines to be able to handle natural languages, presumably, at least on the engineering side, from a perspective of wanting to be able to engage more naturally as humans with the AI that we're working with. And we want to avoid errors and to have that understanding, so to speak, of those machines be as effective as possible. So you mentioned BERT and other advanced technologies that have been coming out in just very recent years. And the fact that they seem to be very successful. So I think part of an implication of your question is, why not just stop where we are? We seem to be doing pretty well, and why, so why keep going? What do we still need to accomplish? And I think an important part of answering that question is that right now we're in an interesting place in NLP where the models really do seem to be doing extremely well, and certainly on many levels they are doing extremely well. At the same time, when you work with language and humans, as for instance I do, we as linguists and cognitive scientists tend to have a particular appreciation for the incredible complexity of language and the incredible nuance and robustness with which humans are able to process and understand language. And so when you evaluate the language processing that machines are doing, even these really impressive models like BERT and GPT 1, 2, 3, and so on, you start to see the places where the capacities for processing language that humans have versus what even our strongest machines have right now do diverge. And you start to formulate expectations for what it would look like to understand language as a human does versus how we see machines processing language. And I think it's very, very important for us to identify the places where we are still seeing gaps and figure out what we need to do to try to continue to close those gaps in ways that really will start to approximate human language processing in ways that maybe are not being picked up by our current evaluations.
Very interesting. Now, what you mentioned about the fact that language is so complex that you somehow have an appreciation for just how complex it really is. That really stands out to me because I feel like it's very easy for humans to take for granted just how complex language is, right?
Absolutely.
we were kind of built, like our brains are structured to be able to handle language. And it sort of goes both ways, right? Language affects the brain affects language. Of course, I mean, one of my favorite examples actually is, I believe it's if you speak Russian from a young age versus if you speak English from a young age, you can differentiate between more shades of the color blue. I believe it is because there are more words for blue in Russian, right? And it's fascinating to me how a different language can quite literally change the way that you perceive the world. And there's so many sort of emergent phenomena that come from language that we don't even realize that sort of hint towards that more complex structure behind that language. Things like Zipf's law that are really interesting, right? And sort of what I want to ask you in when it comes to natural language processing, I mean, you mentioned that there are certain things that these language models just cannot do, right, today that humans can do very, very easily. One of those in specific that I'm very interested in is common sense reasoning, right? Today we see there are lots of different language models that are great at certain tasks, but then they kind of break down when you ask them to try and reason or you give them a task that requires some kind of common sense reasoning. Things like maybe have you taken a look at what's called a common gen data set by any chance? It's a pretty
I'm not
obscure
familiar with
one.
that one.
No, okay. Well, there are all sorts of data sets. There's ones that I'm sure you are familiar with, things like the swag data sets and these sorts of things. But then there's also like the common gen data set, which is, given a set of concepts, can we create a neural network that could like stitch together those concepts into a sentence, right? So like dog, frisbee, catch and throw. Could we say a human threw a frisbee to the dog that catched it, or something of that sort? So, my question to you is, what are we doing in natural language processing today to be able to work towards models that can better reason? And also, what are the challenges with that? Why can we not already do that today with today's language models?
Yeah, so I'll start by saying sort of predominantly what the predominant approach is right now in natural language processing that has been producing all of these really impressive looking successes that you've been mentioning and that we've been mentioning. And then I'll try to tackle sort of what's so challenging about covering reasoning, though I don't know that I'll have any solutions to propose. So the predominant approach that has been yielding so much success is, as you've been saying, using language modeling essentially, which is taking advantage of massive amounts of completely unannotated data. The more data, the better, where the objective that the learning signal that the model is using is basically just trying to optimize its ability to estimate probabilities for words in context. So intuitively speaking, you can imagine why this is something that would be a useful type of learning signal. So you can imagine a sentence like, I like to eat blank with peanut butter or something like this. And there's only so many things that you can eat and really only so many things that you can eat with peanut butter. So you can imagine that by predicting words in this context, you're not only going to be able to guess what types of things would have these properties that would allow it to be eaten and be eaten with peanut butter, but also from a perspective of the syntactic structure of language, you're also going to be learning things about what types of words can occur in these types of fine-grained contexts. So this is, at a high level, part of the reason that models that are trained in this way are able to be so successful in learning really quite a lot about language as far as we can tell. Now, at the same time, there are some interesting ways in which sometimes so there are some things that these models are really good at, which is specifically predicting words in context and knowing what types of words will occur where and what types of words will co-occur with one another and whatnot. And you can then probe these models to try to see how much they're able to reason, so to speak, by, for instance, giving it a sentence and having the model try to complete the sentence and say, okay, how much was the model able to reason about things and decide what was the best ending to that sentence? This is a fairly indirect way to try to probe for reasoning, though, and in general, this type of training of models is an indirect way to try to train reasoning in general, because these models aren't being trained to reason. They're being trained to predict words in context. They're being trained to pick up on lots of fine-grained and complex statistics in their input. Reasoning really isn't part of the equation in the sense that we tend to think about it with humans. And so when you go about looking at how well the models are able to complete sentences, or for instance, you give it a prompt and then have the model generate a long completion that in some cases look really, really impressive. It still isn't really the same thing as reasoning, because we can step back through the way in which the model was trained, and really it's just doing what it was being trained to do. It's trained to use statistics to figure out what words should come after what other words, or should come in context with these other words. And it's doing this based on a massive amount of data and a massive amount of parameters, and it's doing so in a very impressive way. And it seems like internally this does teach the model a lot of interesting things about the properties of language, but I'm not sure that the type of thing that I would think of as reasoning is necessarily coming into play at all. What is probably coming into play is the model learning how to represent certain types of properties of its input. In addition to being able to make predictions, these models can be fine-tuned to do particular types of tasks based on the features in those models, the learned pre-trained features. But in general, not that we really have a great definition of what reasoning looks like mechanistically in the human brain, but I really wouldn't qualify what these models are doing as reasoning, really at all.
I completely agree in the sense that, when it comes to, for example, being able to fill in the blanks, right, with which is the sort of popular method of training these mass language models, right? So things like BERT, or an example that I really like is Google's T5 network. And the reason I like that so much is because they were able to train that network to do nothing but say, all right, this specific span of text is going to be masked out, and the decoder of the transformer just needs to predict that span of text. And suddenly they could retrain that network to do closed book Q&A. So, they're not feeding it any data to extract answers from, they're just getting answers from the weights of the network. So the network is quite literally doing exactly what it was trained to do. It is doing fill in the blanks, and it's really good at that because it's using its many hundreds of millions of parameters to memorize a lot of that data. Right? It's not doing real reasoning, or at least then again, as you mentioned, it's not like we really know what real reasoning means. We don't have a very clear definition of that. But it wouldn't really qualify for what I believe, at least you and I would count as reasoning, right? It wouldn't be able to generalize and be like, hey, apples and pears are fruits. You could pick them both off of a tree, and you could put them both in a basket. It's got to learn them separately for each one. And there are some really interesting patterns that they pick up on, but at the end of the day, they're still incapable of some pretty simple reasoning tasks, right? That I think are pretty integral to how we understand language as humans, right? Because that's intertwined with the way that we see the world. Now, another thing that I think is really interesting is the fact that because these models are not capable of that reasoning, but because they can generate such realistic natural language, sometimes it can be hard for us as humans to sort of tell that difference between a language model that isn't really reasoning of any sort. It's just predicting the next word and sort of, as you mentioned, statistically generating language, versus the real thought that goes behind the sort of natural language that we write as humans. So sort of moving on from there, I wanted to ask you a bit more about the work that you've done in language. I mean, you mentioned being able to probe language models and being able to sort of figure out what patterns that they learn. Could you tell us maybe a bit more about that technology and some of the other research that you've done when it comes to natural language processing?
Yeah, of course. So there are a couple of lines of sort of probing and analysis work that I've been doing to try to get a better handle on exactly what types of linguistic information and linguistic capabilities these models are picking up on. Because the way that this tends to go is one of these models comes out, it's behaving in really impressive ways. People are sort of blown away for a while. We want to know, okay, well, did this model solve it? What exactly are we looking at here? What are the weaknesses? Where do we need to go from here? So there are a couple of lines of work that I've been talking about recently. One is early on, before we had BERT and these large pre-trained language models on the scene, people were interested in trying to design recurrent neural network sentence encoders. So we had done quite well with getting word level generalized representations that you can then just stick into models and and then have those allow for generalization over sort of word meanings and word properties. We wanted to be able to do that with sentences too. So people were designing these models, and they produce vector representations, and then we want to know, well, all right, we have vector representation. It seems to be decent at determining how similar two sentences are to each other, roughly speaking. But have they captured the types of complicated sentence meaning information that humans are able to, right? So humans process sentences. They can figure out a lot of things based on, as I'm saying sentences to you, you're able to extract a lot of information out of those. And in particular, so you mentioned a few minutes ago, examples of just taking concepts, sort of disconnected concepts, putting them together and formulating a sentence. You mentioned a dog and a frisbee and maybe a boy, let's say.
Catching and throwing, yeah.
So the interesting thing about these types of disconnected concepts is, although as humans who have common sense knowledge and experience in the world, we know that if we have a boy, a frisbee, and a dog, probably the type of scenario we're talking about is a boy throwing a frisbee for a dog in a game scenario. But the interesting thing about language is we could also formulate sentences like the dog threw the frisbee for the boy, or the frisbee threw the dog at the boy, right? I mean, we can formulate all sorts of nonsensical sentences. And each of those things that I just said, you also understood what those meant, right? Mm-hmm. Because you are a fluent speaker of this language that we're speaking right now. And so you're able to tell that I'm describing a scenario that you've never heard of before. It's completely bizarre, but that's the way that language works. It's extremely expressive and flexible. So the reason that this is possible is a property called compositionality in language, such that you can just take all of the parts and use the rules of language to put them together into a meaning, even if it's a meaning that you've never heard of before. So this is one way in which the types of statistical properties of these languages may deviate from the way that humans work, because if those models are relying primarily on what usually happens, they may fail at some points to pick up on sentences that are describing something that is sort of in that long tail of the distribution, or that just never happens at all. So one of the things that I was interested in trying to understand with these models is, to what extent, as they're processing these sentences and these other larger inputs, to what extent are they using a compositionality concept that resembles what humans are doing? To what extent can they pick up on this sort of systematic information that can be disentangled from statistics of how sentences tend to look versus what this actual sentence is saying? And so in this case, what I was doing was I was using something that has come to be referred to as probing tasks, where you take the internal vector representations learned by these models, and you train a simple classifier that takes those vector representations as input, and you try to train the classifier to do some kind of task that would involve extracting some key type of meaning information, or any type of information, but for me, I was interested in meaning information from those representations. And basically the way the reasoning goes is, if the classifier is able to extract that information, we're going to conclude that that information was somewhere in there in those sentence representations. There are a lot of complications there, because there are other ways that the classifier may just pick up on little bits of information in those representations. So we put a lot of work into trying to control the variables in the sentences that we were using for this classification task, to try to make it, to the greatest extent possible, necessary for the classifier to actually be picking up on the meaning information we were targeting in order to do well in the classification task. And we found some interesting things there, in particular looking at semantic role, which is who did what to whom. So we're looking at, if we just took boy and dog and frisbee and averaged those words together, most likely, we know most likely what's happening in that scenario. But if the actual sentence was that the dog was throwing the boy at the frisbee or something like this, we want to know whether the model was able to pick up on those sorts of distinctions. And what we found in that original study was that these sentence encoders really were only marginally above chance on a well-controlled task of this kind, in terms of being able to distinguish between these. A bag of words model, which was our control, where we just literally do average those words together, can't distinguish word order, was at 50% chance as expected. But even some of these other models, including the Infercent model, which is a Facebook model trained on natural language inference, was also at 50% performance in distinguishing those things. So this, I think, is one of these examples of where we can try to sort of tease apart the types of statistics that the models may be relying on that make it look like it's doing really well, versus the types of capacities that we know humans have that we want the models ultimately to be able to have. So this was an earlier study studying these sentence encoders, moving on to these language models that we've now been talking about with BERT and everything, these types of models. So that was studying the internal representations, not looking as closely at the sort of output behaviors of the models. So if there's a certain type of information in a given internal representation, the model may or may not actually be using that information when it's producing its outputs, producing its predictions. So we can get around that by designing tests that look specifically at the types of word predictions that the model is making in context to see what types of information it's using to make those predictions. And so another line of work takes tests that were originally designed for studying human processing of words in context and says, all right, well, we can use this same type of test and apply it to these models, which similarly are able to take a context and then produce predictions for what types of words should go in that context. Humans are able to use certain types of information. Are the models able to use other types of information? So a standard example, he caught the pass and scored a touchdown. There was nothing he loved more than a good game of. This particular example has the word touchdown in it, which is a very strong cue for the completion football. But these are the types of sort of long and slightly oblique references to a particular type of situation where humans are able to complete it if they have the relevant vocabulary and common sense knowledge. And the question is whether the models are going to be able to. BERT is great at that sentence, but there were lots of other sentences in the data set that the model struggled with more. Pablo wanted to cut some lumber, so he asked his neighbor if he could borrow her. And you see a bunch of things that a person might borrow but have nothing to do with cutting lumber, etc. So these are the types of tests that can start to sort of tease apart what types of common sense knowledge has the model been exposed to, what types of things is it able to make use of, what sorts of fine-grained distinctions is it able to make, and which ones is it not. So these are sort of two types of ways of trying to dig a little deeper into the linguistic capacities that the models have gained over the course of their training.
Very interesting. Now, it's so fascinating to see the patterns that some language models are capable of picking up on if they were trained with the right objective, right? So you mentioned the sort of previous language models or sentence encoders that we would train, weren't capable of picking up on these tasks. Were only marginally better than random chance. That was really interesting to me because actually maybe a good example to make this more relatable actually, based off of a video that's actually already on my YouTube channel. Something that's really interesting is the unsupervised sentiment neuron that OpenAI discovered when they were training their Amazon review generator, right? So they were able to take the internal hidden state from their LSTM and sort of train a classifier to be like, all right, is the review positive or negative in sentiment? And the classifier was literally only looking at a single output from that hidden state, and turns out the internal hidden state had learned sentiment without ever being trained on it because it was useful for generating reviews. And we knew that that the model was actually using the output of that neuron, or the output of that of that specific dimension in the hidden state, because when you actually modify it, the output of the review is either positive or negative depending on how you manually change it. So that's really interesting stuff, right? To think that neural networks are implicitly learning all these different pieces of knowledge that they were never trained on because the training objective that we were giving them sort of forced them to need to learn this to be useful at the actual training objective. Which almost actually makes complete sense, because when language models are not doing common sense reasoning very well, it's not the model's fault, right? It's our fault because we haven't given them the right training objective.
or we haven't got the right model. Yeah.
Exactly. It's not like the math is wrong. It's not the right math. We're not doing the right we're not using the right objectives. The objective at the end of the day is how the language model is going to figure out, or the neural network is going to figure out what patterns it needs to pick up on. And so that actually brings me to almost the future. What are we doing to figure out better training objectives? Because the thing that I'm sort of thinking about is, let's just say we're training an image classifier. I mean, the output is just a label. Like, you feed it an MNIST digit, it's a label from 0 to 9. And it's pretty simple for us to say, if you predict 0 and we fed in a 0, that's the right label. So putting an objective there is really simple. And even then, we can really engineer that training objective. Do we want to do softmax cross entropy? Do we want to, we can still engineer the specific math behind the objective, but the idea behind the objective is simple. It is, can it predict a 0 or a 1 or a 2 or whatever? But when it comes to language, again, the whole reason that neural network models exist is because humans can't manually write the mathematical functions to do this pattern matching, so we train neural networks to do it for us. But then even the output of these neural networks is still language. So how exactly are we training these objectives to, or sorry, how exactly are we sort of engineering these objectives now? And what do you see as some of the work that we're doing to solve this problem?
Yeah, no, absolutely. I think this is one of the key questions is sort of what are we going to need to do? What type of learning signal is going to help to guide these models to learn all of the broad amount of information that we want them to learn, namely all of the nuances that humans are able to capture? And also what types of models, importantly, we also potentially aspects of the models are going to need to change. There's lots of talk, of course, about trying to build in certain inductive biases into the model such that the learning process, not all of the burden goes on the learning process and on that learning objective and on the training data, et cetera. Which is something that is very difficult to do well. And typically nowadays we see that larger models, more data tends to beat efforts at sort of building in knowledge into these models ahead of time. But yeah, so there's a number of different ways that people think about formulating these objectives. At the moment, as we've mentioned a few times, this language modeling objective seems to be the most successful. And there seems to be a couple of reasons for that. One is that you can train on just a ton of data without needing to impose any sort of human-guided annotations that can or will inevitably be imperfect. And that will necessarily reduce the amount of data that we have because you're never going to have humans annotating the entire internet for you, whereas you can potentially train models on the entire internet. So the language modeling objective, in part because it allows you to have a ton of data, is the front runner at the moment. Probably another reason, though, is that genuinely trying to predict words in context for some of the reasons, non-exhaustively for the reasons that I was mentioning with eating and the amount of information that you get from context. That really is quite a lot of sort of various levels of information that you are bound to pick up on that will help you to optimize an objective of that kind. Now, the other question, though, is sort of what other types of tasks might help us with learning language in a way that sort of moves away potentially from purely trying to predict words in context and picking up on those particular statistics. One type of thing that's particularly appealing is the natural language inference objective, NLI, also known as entailment, which essentially says, what are the logical consequences of understanding a sentence? So if I say, I have a poodle, right? You know that this entails that I have a dog because all poodles are dogs, right? And so this is a particularly strict logical construal of entailment. Entailment tends to be a little bit broader in the NLP domain, but this is the basic idea. And this is something that really you would think would be a great way of training models, because this is just the type of thing, if they're going to perfectly do the entailment task, you would think that they would really need to pick up on those nuances of what a sentence means and what the necessary inferences are from those sentences. So in principle, NLI is an example of something that seems like would really be a very useful and valuable learning signal for learning, for guiding models to end up learning meaning based on the optimization of that objective. I think that that's still the case. We haven't gotten to a point where because of course NLI is something where you do need human annotations. There's a lot of human error involved and a lot of sort of human trends involved in gathering those annotations. And so we tend to find that models that do well on the current NLI benchmarks that we have aren't necessarily being forced to learn to do NLI in the way that we would like them to do. Rather, they're probably picking up on sort of more superficial patterns in the data that allow them to do a good job at giving the correct label without necessarily really having had to solve the task. And this is a very difficult problem in the field in general right now, but it is another example. So sort of setting that caveat aside, that right now we really haven't perfected that as a way of leveraging that as a learning signal. That is another type of learning objective that seems like it would be a very useful type of signal for training these models to learn meaning that does differ from language modeling. But again, it suffers from the limitations of these types of supervised annotated sorts of learning signals. So yeah, I think this is really a problem that we're trying to solve as a field. And I think a lot of people are hopeful that the language modeling objective that has been showing such impressive outcomes may actually be able to get us all the way. I think that we're likely, as we continue to explore the strengths and limitations of these models, we're probably going to find that that won't get us all the way, that we will need, there will be more to the story, but you never know. Things continue to progress.
Absolutely, you really do never know when there's a brand new innovation that completely changes, the field. That could come up literally any day. Could be today.
Yep, could be
Could
today.
be. Back when Google released that paper on BERT and their newer results, that completely changed the way we think about language models. And to this day, it completely has changed the way we think about this stuff. Maybe actually a good way to think about this would be an example from an application I built a couple of days ago around Tetris, and it's a completely different domain, not even using remotely the same math even. But the concept, I think, is very similar. In the game with Tetris, you have two ways of winning, or not winning the game, or of getting a high score in the game. One of them is by just continuously clearing lines, like just clearing as many lines as you can possibly clear. Right as you get a line, just clear it. The other way, which is the more efficient way, which is sort of the human way, is stack up 4 lines and clear 4 lines at a time. That gives you many hundreds of times the score of just clearing a single line over and over again. But when you train mathematical models to take a look at different heuristics and try and score boards, they almost always overfit to just, clear as many lines as you can possibly clear greedily. And that's because the models realize, well, it's so much work, and I'm sort of humanizing the model here, but that's just a limit of language, right? They realize it's so much work, meaning that minimum is so far away to figure out, specific scores for heuristics where we're able to, clear 4 lines at a time. So why not just clear as many lines as possible and just keep it going infinitely, therefore we get a really high score. Right? So the model isn't learning what we want it to learn because the objective isn't right. Even if it gets, greedy, we're still giving it a high score. So it's like, that's good enough. Even if I could get a higher score in less moves by doing something else, why would I want to if I could just keep this going infinitely? Right? So it doesn't really have that incentive to go all the way out in that space of heuristic vectors to try and figure out what the best way to get Tetrises is. Similarly, I think, we have that sort of natural language inference or that entailment task where, even though you would think that the model would be sort of forced to pick up on actual sort of cues that require reasoning to be able to figure things out, it's still mostly just kind of taking a look at the words and the sentences and little syntactic patterns and trying to, do a best effort based off of that, because it's like that's good enough, and just sort of falls down to that minimum and doesn't ever get back up and try and find another place in the weight space where, it's actually doing reasoning, because that's just too far away. So again, it's all about, can we figure out the best data to feed the models? Can we figure out the best training objectives to use that data and the best architectures for these networks? So definitely a huge challenge, and who knows? Maybe the real answer is a hybrid approach between all these different approaches.
Yeah, that may be. And the Tetris example is an interesting one. And I think with games, there's this interesting difference there, because in the case that you were describing, you have a very clear sense of what solution would be better and sort of what the model is doing wrong. And so there are presumably ways, either via the objective or via the model, that you could sort of guide the model toward dispreferring solutions where it's clearing each individual line once, such that it is forced to learn solutions that maybe are more human-like. In the case of language, often we don't have such a clear sense of what it is that's missing, right? It is very helpful to be able to draw on what cognitive scientists and linguists know about language, but there's still so many mysteries, and language is so complicated. There's really just a lot that we don't necessarily understand about what the solutions that the model would be better off with actually are going to look like. And so this is one of the things that makes this challenging, in particular with natural human language.
Wow, I love that extension, because you are right. I didn't notice that, but I had a very clear sort of objective in my mind as to exactly what I want that model to do and what I want that model to learn. And as a matter of fact, you are right, because I had that very clear objective. I was able to do a couple of things, like, for example, force the model to keep certain heuristic weights positive and force some to be negative, right, which I know would sort of lead to a better solution. Or maybe, make it so that the training objective, takes into account how many moves it made and cap the number of moves it can make and try and, get it to get as high of a score within a certain number of moves. So there are all these different things that I could do because I knew exactly what I wanted, and I was able to very clearly define the math for that. But then with natural language, we don't have that luxury. And again, I feel like it comes back to my previous point. If we did, we wouldn't really need neural networks anyway because we could have written those mathematical functions ourselves at that point, right? If we really understood language down to a mathematical level like that, we wouldn't need these complex language models in the first place. So it's sort of like a, maybe it's a bad analogy, but kind of like a chicken and the egg problem where it's like, which one came first, right? Can we understand language with neural networks, or do we need to design the training objectives first? So it's really interesting to think about all these different, challenges. And actually, we got a question that I think fits right into our discussion here. And that question is about visual question answering. So being able to answer questions on images. That's also something that really fascinates me. And I do know I've taken a look. I believe it was a talk from Christopher Manning, but I'm not sure if it was. But I think it was. And the talk was, and one of the examples they had shown was when you train a visual question answering system on a certain set of data, but then you change the data distribution. So, for example, if the previous most popular sport was tennis, and you change that to hockey, and you completely change the distribution of data, suddenly these VQA models are not necessarily garbage, but they're really, really bad at answering questions, right? And so these models aren't necessarily learning the reasoning, but they're figuring out how to cue together maybe a couple of visual clues, maybe a couple of words from a sentence and give an answer. So have you done any work, not necessarily in VQA, but related to VQA? And what do you think the role of VQA is in this whole sort of thing that this sort of journey we've been putting together?
Yeah, so I myself have not worked directly on VQA, so I won't be able to comment in a lot of detail on the particular work being done there, but absolutely what has been pointed out there is very much in line with the types of things we've been talking about here. When you have a different looking distribution at test time, and these models have been fitting to a particular distribution at training time, that's where you start to see these flaws in the way that the models have solved the problem. Sort of like, as I was saying, with the models that are accustomed to people throwing frisbees to dogs and then are encountering instead different types of scenarios and different types of ways that those words are fitting together. So yeah, absolutely. I've been exposed to just a bit of work from colleagues talking about doing similar types of sort of adversarial testing on VQA models and showing that it really does look like when you're seeing high performance, and this was maybe a couple of years ago now, so I don't know how things have progressed since then, since I was speaking with this colleague, but at that point it really was looking like the successes that they were seeing were based on pretty superficial heuristics, and you would see pretty big gaps when you started subjecting these models to more adversarial types of inputs. And so absolutely, VQA, like many other types of supervised tasks, is very much susceptible to models looking like they're doing very well, and then it turning out that once you test with adversarial inputs that don't necessarily reflect the precise cues of the training that the model may have latched onto, you start to see a lot of weaknesses.
Mm-hmm. Now, actually, you mentioned the adversarial examples, and completely different, but this reminded me of something else: generative adversarial networks. Now, GANs, personally, whenever I've implemented GANs, they're both elegant and inelegant at the same time to me, in the sense that it makes so much sense that you would want a neural network to generate and a neural network to discriminate, because then it's almost like that issue of the training objective, us not knowing how to architect that, we kind of offload that as well to a neural network, right? So we're kind of offloading that other task to the network as well. So that kind of helps us out a lot with images and sort of like tabular data, these sorts of things. But then we come to natural language, and GANs don't really perform very well at all. And my question is, why? What are some of the reasons that GANs don't perform well on natural language today?
Yeah, I haven't done a lot of direct work with GANs and with natural language, so I don't know that I can give too much of an answer. But I will, I think, comment instead on this basic comment that you made about trying to offload to a network that is going to just learn all of the different features so that we don't have to worry about this, because this is something that has come up already a couple of times, and I wanted to make sure to get to it. This is sort of the basic idea with these large models, that even as we learn a lot of things about human language, are we going to be able to use models that are able to pick up on tons of features from huge amount of data, and are they just going to sort of do all of the work for us? And I think that this is a really interesting idea, and I think to a large extent we may be able, I think that we can harness this type of power to make this work. But exactly as you've been saying, this is going to require that we recognize what types of learning signals are going to force those models to learn things in the right directions, rather than just picking up on sort of more superficial types of features in the input and in that training, in the case of supervised tasks. So yeah, again, I can't really comment too much on what's going on with GANs with natural language, not having worked directly with them myself. I don't know if I have too many insights, but in general, this concept of having some type of network that we think is going to be able to pick up on a lot of things that we just didn't want to have to try to define ahead of time ourselves. What ends up happening typically is that while they learn a lot of really interesting things, often once you sort of pull that curtain away, just as you've said earlier, they're really learning exactly what we trained them to do. And sometimes that's what we want, and sometimes it's not quite what we want.
Yeah, it's even though it's technically, again, it's not the math's fault. Fundamentally, the math is right. It's just that's not the objective we want, right? So I referred to this article by my mentor Timothy Duncan a lot of times throughout the series, and I feel like it comes back again because objectives are so important. It was an article about I believe the title is A Tale of Two Police Departments or something on those lines. And the article was about, how in the U.S., the incentive for police departments for the war on drugs was make as many arrests as possible, and that led to the state that we have today of the police departments, where, it's about that training objective, because if that objective is wrong, then, fundamentally the model that you're training is going to take the easiest possible way to achieve that objective. And if
whether it's wrong or right, it's going to take
exactly. It doesn't matter whether it's wrong or right. The model doesn't care about that. The model doesn't know that. That's not fed into it. That sense of right or wrong. The model just cares about, did I reach the objective? And if there's a really, really easy way to reach, not even necessarily reach, but get good enough at that objective, that's all the model cares about. Well, that could be in real life, that could be with police departments, that could be a team that you're managing, right? If you don't have a very clear objective, you're just going to end up finding the easiest way to get to whatever objective you end up defining, or even language models and neural networks, right? If you don't have the right objectives, you're not going to get the right output. So that was the original question about VQA, in case I forgot to mention the name. That was from Soumya, so thank you for asking that on YouTube chat. Now, another question, this one's from Joshua. On the YouTube channel as well. He's saying, what's your take on OpenAI's model for natural language processing and computer vision? So I'm going to assume that he's talking about GPT-3 because that's the one that they also trained to generate images very well. So what are your thoughts on that? And if I may add something to Joshua's question, what are your thoughts on this sort of just continuously scaling up fundamentally the same technology, right? So it's still maximum likelihood estimation. It's still just predicting the next word, but they're doing it 100 times larger and with a lot more data. What are your thoughts on that? Do you think that's potentially a way we're going in the future, or do you think we need smarter models, not models that work harder?
Yeah, it's a great question. I haven't had a chance personally to play around with GPT-3 yet, and so I haven't had a chance to see, like, where might we be seeing some weaknesses of the same types that we may have been seeing with the predecessors of GPT-3. I can say that when GPT-2 came out and had this, for those who aren't already familiar, there was in particular this unicorn passage where there was a human prompt of a sentence or two describing the discovery of some unicorns, and then the model produced this really impressive looking generation of a fairly long passage that at least at surface level looked like it could have been generated by a human, though when you look more carefully you see some sort of contradictions in terms of the sort of common sense of the passage. But it was this really impressive looking outcome that inspired in particular my use of human tests to sort of look more closely at exactly the types of information that models like these are able to make use of when they are doing these generations. Now, one thing that I can say, I had a student kindly run GPT-3 who on some of the things that we had tested BERT with these diagnostics that are based in human tests. And one thing that was really, really stark in the results of those tests was in use of negation. So things like not and didn't. So we have sentences like, a robin is a, you have the model complete, and the model is really, really good at taking what we call the hypernym, the sort of higher level category to which that word belongs, in this case, bird. A robin is a bird, and associating the noun with that. So within the top 5 completions, the model 100% of the time for all the sentences we gave it was finding the correct completion. Now, the trick is when we insert a not. We say robin is not a, right? So now we have sort of a really wide range of things that are potential completions, but a human who knows what not means knows that really anything but the things that a robin is are appropriate completions in this case. And this is not the way the model behaves at all. And this is not all that surprising given that it's just trying to optimize its probability distribution as well as possible, and having just sort of like the entire vocabulary other than bird isn't particularly helpful for it in a case like this. But what we do see is that 0% of the time does it assign a higher probability to a true completion like tree, a robin is not a tree, versus a now false completion. Wow. Bird. Yeah, so this was the result with BERT. And I haven't run the entire diagnostic on GPT-3, but again, the student sent me some sort of preliminary results with some examples from the paper, and it seemed to be showing a similar type of pattern such that it does not drastically change its probability distribution in the same way we would expect a human to, given that they know what not means. So this is one of the starkest sort of results that has come out of these types of tests. And in thinking about sort of how are things going to change as we move away from BERT, as we just make the models bigger, as we just make the training more robust, what's going to change and what's not going to change. I think that as the models have the capacity to memorize more stuff and form sort of more complicated representations and more abstractions, there are certain things that are going to change and certain things. So some of those diagnostics involve, like we gave the lumber example. Mm-hmm. Apparently, according to the student, GPT-3 is handling Pablo cuts the lumber example. And this is exactly the type of thing that you would expect. Well, now it has a better handle on what cutting lumber involves. It involves a saw, so probably the completion here is going to be saw. This is sort of just the type of thing that you would expect a model that has done more memorization, just general facts and vocabulary, would be able to handle. But this negation example is something that seems like a more fundamental divergence between the types of things that this objective is going to be well suited to and the types of things that we want models to be able to handle if they really know what the meanings of words are. So I think that this is exactly the type of thing that we want to get a better sense of. What sorts of things are going to continue looking better and better as the models get bigger and memorize more things and are able to store more in those parameters. They're going to look like things that involve having access to tons of situations and being able to memorize things about those situations and being able to know what sorts of words end up in what sorts of contexts at a very complex and sophisticated level. But the types of things that the model doesn't need or is better off ignoring in order to make better predictions in context, those are the types of things that it's probably not going to learn, even if you add a ton more data and a ton more parameters. So that's probably where I would draw that line.
Wow. Okay, that's a lot to unpack. So that's what specifically fascinates me is that there are some things that we would expect these models to be really good at, which, for example, cutting lumber. You would expect that GPT-3, being 100 times bigger and being trained on so much more data, of course, it would know some things about the world within its weights because it has the capacity to store that information, right? It has the space to store, and it's useful to achieve its objective for it to be able to store that if you're cutting lumber, then you're going to use an axe, right? But then there's some more general say reasoning, right? That's required when you put a not there. That's like, oh, a robin is not a tree or a house or a computer, whatever, right? It could be anything but the things that would be there if there were no not. That it's really fascinating to see that the models struggle with that, because it really, really shows off that whereas, that the training objective may be working towards helping us generate what looks like some realistic natural language, that doesn't mean the models actually understand anything about the world and are doing anything more than just statistically, figuring out, hey, based off of these words, I think this should be the next word.
Exactly.
Right? If they were actually doing that sort of multi-hop, but being able to hop through, different concepts and how they relate to each other, it would have been doing better at that not example and many other examples. But I can't wait till you get to do some more in-depth testing on GPT-3, because I think it would be interesting to see where those limits lie. Actually, this reminded me of something else. This is something that just came to my mind, and I'm pretty sure there's some work being done on this, but I wanted to see if you have any thoughts on it as well. And that is that, we don't necessarily have a very good, differentiable training objective that we could give to these models for them to, for us to be able to tell them whether or not their natural language makes sense, right? Their completions or their generations or whatever it is. And another environment where sometimes we don't necessarily have a perfect explanation, right? Training signal for everything the model does is games, right? Like in Pac-Man, we can't say a move to the left was objectively good or objectively bad, because it really depends on the game state. It's a pretty subjective evaluation. Like within the game of Go, for example, you can't necessarily objectively say a certain move is excellent or a certain move is really bad, even though we can generally come to a consensus, because it depends on your style of play. And so that's where we use reinforcement learning. So, have you seen any work that's really interesting towards being able to understand natural language with reinforcement learning? What are some of the challenges there? What do you think some of the interesting possibilities are there?
Yeah, I think there are definitely some interesting possibilities, and certainly people have been messing around with using RL for particularly games, but also to an extent for natural language. Not being one of these folks, again, this is one of these topics that I won't be able to say too much about, but I will say that it isn't a paradigm that I've been seeing sort of breaking so much into the mainstream of natural language. I don't know if I necessarily anticipate that that would be sort of the direction that we would be going ultimately. But again, you never know. It may just be that we haven't sort of explored that domain enough, sort of found the tricks to get that working in such a way that that's going to help to complement some of the weaknesses of the predominant paradigms right now that people are using a bit more often. Yeah, I'm not able to say too much about RL in this domain, not having worked as much with that, but I think that sort of there are a wide variety of different sorts of solutions that we can explore, and that's definitely one of them that we should consider.
Very nice. Yeah, it kind of makes sense almost that we would want to use something along the lines of reinforcement learning, because I mean it's pretty. I wouldn't say it's the same or even similar, but there's a parallel, right, to the challenges that we face in something like games versus natural language. We can't necessarily say in a game why a certain move was necessarily good or bad. We cannot give the model a direct training signal based off of that. But same thing in natural language. We can't really say, hey, that saw completion for the lumber thing, this is exactly why that was great, versus, you could also technically put axe there and that would also be correct, right? I mean, it makes sense, but because, in today's language models, because that's not what was in the labeled training data, the model's going to get a bad training signal for that, and that's not good, because that was technically a good final objective, right? That was a good final completion. So our objective right now is going to be like, hey, that's not what was in the training data. So even though the language makes sense, we're going to give you a bad training signal because of that. So same thing within reinforcement learning. We can't necessarily say good move, bad move. It kind of makes sense that we would want to have a reinforcement learning type training objective for the natural language, but we'll see.
That may be. It may be that this is a direction that's promising for us.
Potentially. I can't wait to see what we do there. Now, we have talked a bit about the technology behind natural language processing. Now we're getting a couple questions from students in the audience as well, specifically from Tassin and Somya. They're asking, what skills do you need to work or study natural language processing, and why and how should students learn it?
Yeah, great question. So, right now, predominant approach to doing natural language processing involves using machine learning. So learning the basics, the technical details of machine learning is going to be a really useful way of proceeding in order to work with natural language processing. Now, as a linguist, I would be remiss if I did not also say that it's going to be also useful to have a sense of how complex language is and what types of phenomena you're going to want to be able to capture as someone who's trying to build successful, robust natural language processing systems. So knowing something about language in humans, having taken some fundamental linguistics, I think is also a useful type of thing, so that you have some domain knowledge to work with in addition to just throwing machine learning models at some data. Yeah, so I think that there are a lot of useful resources out there for getting started with natural language processing, lots of really excellent textbooks. uh, in addition to basics of machine learning, sort of moving to other basics of probability, basics of linear algebra, calculus, things like that. These are going to be some of the mathematical fundamentals that are going to be useful for these types of things, not just for natural language processing, of course. Let's see. Yeah, so I think sort of a combination of this technical training, working with machine learning, and also having an understanding of how language works in humans, because I think over and over again you see that the more people have an understanding of language from the perspective of of sort of the science of language, the more of an appreciation people have for how hard the problem is, and the more people tend to be able to pick up on when there are flaws.
Hmm. Thank you for sharing. I'm sure that's going to be useful for all the students in the audience to figure out, where they should be going to actually learn about natural language processing, because this is really interesting stuff, and I would recommend getting into it if it's something that you're passionate about. All right. Now another question. Oh, actually, a question from my end, from my side, really quickly. Um, the question is, well, I guess it's kind of around sort of comprehension and being able to it's sort of like in between understanding and generating natural language, and that is that, let's just say we were to take a look at T5, right? Google T5. It's great at translation, right? It's really high up there, I believe, near the state of the art, or is the state of the art in neural machine
I'm not
translation.
sure, but yeah, I
Yeah,
can believe.
and the one of the things that I think is really fascinating is that auto-regressively decoding, when it comes to language translation, while it does have its issues, right? It still has exposure bias. It still has these sorts of issues. It's a lot easier for the model to do that auto-regressive decoding, and the final generations are a lot higher quality because the thinking was already done by the human that fed in the initial text, right? The actual creative part of what's the message that we want to get across, that's already been fed into the model. Now all it's got to do is, well, all it's got to do, that I'm saying that like it's easy, it's not, but what it's got to do now is comprehend that and go ahead and autoregressively decode a different sort of a different way of representing the same sort of meaning.
Sure.
But when it comes to purely autoregressive decoding with no initial input, with no initial sort of thought that you want to base off of or get the same meaning across, that's when language models kind of start to break down, right? That's when we start to see like the issues that you mentioned around, when you say not, there's, you can't really understand that you've got to completely change the probability distribution because of the word not. So what do you think the future holds for being able to almost pre-plan when language models are trying to generate, right? Like, if you maybe a good analogy would be like generative adversarial networks. Why can they generate images so well? It's because they're able to pre-plan. They're able to pick a specific point in their latent space that they want to generate from, instead of like a variational autoencoder where they've sort of got to average out and sort of make like a blurry image. So blurry in the natural language context would be, nonsensical. So what do you think that future holds? Do you think we'll be able to create neural networks that can pre-plan what it is that they write, so they can actually learn to write?
Yeah, I mean, there are certainly ways to get around this problem in sort of a more directly engineered way, right? You can design a model that is specifically given some kind of discrete representation, and and this constitutes its plan, and then it just produces sort of a generation based on this. This is kind of an extreme version of how this might work. Again, this is going to involve humans coming up with something that they, some sort of meaning representation
Yeah.
indicating what the model should be talking about, and then having the model, produce some sort of surface realization of this. Um, when you have something more along the lines of a latent space representing sentences, and you can sort of sample from this, or the model can sample from this in some way, again, you're absolutely right that you find some sort of messy in between spaces that don't really correspond to normal sentences. But none of these options involve the model doing what a human would do in a day-to-day basis,
Mm-hmm.
where you're thinking, you have sort of desires and motivations and goals and things that you want to convey, and this is what drives what you end up realizing in terms of how you speak. And so this is really a fundamental distinction between the way that these models work and the way that humans work. The models are not formulating their own goals and motivations,
Mm-hmm.
apart from sort of the to the extent to which you can think of the objectives as their goals. They're not, thinking and then producing things based on producing language based on their thought. They're really just reacting and producing mappings from a particular input to a particular output. So this, yeah, absolutely is an important and fundamental distinction here. When people think about models working in more of a free-form way, they tend to think about chatbots as one example of this, because of course, this is the type of context in which humans operate. You get some sort of input from another human, you process it in some way, determine what type of response is satisfactory based on what you want and what they said and all the sorts of different goals you might have in this conversation. There's no reason to think right now that the way that dialogue agents, the chatbots work right now is the same way that humans do. It's really a much more superficial level at which these types of things are working. But absolutely, this is really a major way in which sort of the way that artificial intelligence works differs from the way that human intelligence works at the moment.
Mm-hmm. I feel like that is a pretty fundamental sort of step that we got to take, as to being able to allow language models to have that sort of pre-planning stage, right? Being able to say, not only here's the next word that I want to generate after these words, but here's the overall objective that I'm working towards that I want to generate, and now I'm going to figure out what the words need to be. I think one really interesting example would be the Optimus language model for Microsoft research, where they were actually able to take a sentence, feed that into BERT, actually take a small vector representation of the encodings and feed that into GPT to have it autoaggressively decode. And because of how small that vector representation was, they were kind of forced to compress meaning down into that vector, feed that into GPT, and now they can do sentence level analogies, right? So they can say, my dog likes the red ball, my dog likes the yellow ball, then feed in my cat likes the red ball, and what's the analogy to that, right? So it's interesting to see what different folks are working on to solve that problem, because that's a pretty fundamental thing. If we want computers to be able to talk, or not necessarily talk, but write language, right? They need to be able to pre-plan what it is that they want to get across. All right. So now we get another question. This one's really interesting to me. So this one's a little bit less on the actual NLP side, but it's more on the implementation of the NLP and of the technology that goes behind it. And it specifically has to do with programming languages. Cecily is asking on the YouTube chat, she asked specifically, is Python the best programming language for NLP tasks? But I'm going to actually bring that up a level and ask, what language do you think would be the future for machine learning tasks?
Yeah, I don't know that I can comment on sort of what might be the optimal language for machine learning in the future.
In your opinion.
I can say that sort of empirically speaking, right now Python is by far the dominant language that we're seeing being used by researchers at the moment for natural language processing. If you want to work in NLP, there's a good chance that you'll be using Python. So at the moment, that's sort of where the field has gone, whether that is sort of the be-all, end-all, whether this is really the optimal approach, or whether this is sort of a result of convenience. This is, I don't know that I am able to comment on that, but yeah, right now, sort of from a practical standpoint, people are primarily relying on Python.
Right, and I feel like there is a lot of room for improvement, definitely, right? I mean, personally, compilers are something that I'm fascinated by as well. There's language machine learning, but there's also compilers that really interest me. And as a compiler person, when I look at something like Python and how we try to use machine learning frameworks in Python, I kind of think to myself, there's so much of a better way we could be doing this. And so, great example, compilers are meant to facilitate the programmer, right? Like a couple days ago, and this is actually I think a pretty good example, as I was working on that Tetris app and trying to figure out the rotation for the pieces, one of the pieces of logic that I implemented just as like a temporary, let's get this done as quick as possible, implemented a clockwise rotate, and the counterclockwise rotate, instead of negating the signs, I wanted to actually take a look at what the code would be or what the sort of machine code would be if I had told the counterclockwise rotate to just call the clockwise rotate 3 times. And to my surprise, the compiler had unrolled the loop to actually 3 times calling counterclockwise, and then inlined the math and then simplified it down to the original version. So, at the end of the day, the compiler's fundamentally transforming my logic and making my job easier. So if we could do the same thing for machine learning, to have faster machine learning with less code, that's what languages like Julia or frameworks like Swift for TensorFlow are working towards. We might actually have an episode in the future about Swift for TensorFlow, but I do already have an episode, actually very recently, on the Julia language with the CEO and CTO from Julia that were on the show. So that was a really fun episode. I will link to that in the description as well. But there is another question. This one's from Anurag, and this one's actually pretty interesting. This is more of like a use case for NLP. So can we use natural language processing to facilitate language learning for people? So like for actual humans, as we're trying to learn language, can we use NLP technology to help us do that more efficiently?
Yeah, that's a really interesting question. So language learning, especially for adults. So when children learn language, I don't know that natural language processing would necessarily be the right way to do this, because there's a lot of evidence suggesting that human children don't learn language from television, for instance. So probably we want to just don't, if it ain't broke, don't fix it. No need to try to have children learn language from something other than their guardians and other humans around them. But from a perspective of adult language learning, there are a lot of different learning styles. Some people, for instance, find programs like Duolingo and other programs like these to be very useful, and other folks find it easier to just sort of memorize things, memorize grammatical rules and things like this. Other people find it easier just to sort of get a little bit of those basics and then interact with people in a social context. And so from a sort of pedagogical standpoint, I think it's a little hard to know what sort of optimal things NLP might be able to help with, but especially for sort of automated programs like you find online or that you find sold. Yeah, you can imagine ways in which NLP potentially could contribute to that, particularly if you're able to guarantee grammatical grammatical productions on the part of those NLP models. Maybe you can sort of automatically produce, say, language pairs from a translation system that can be used to augment sort of the types of examples that are being provided to learners. Of course, there's a lot of nuance to trying to teach language, so you're going to want to try to have sort of simpler examples for beginners, more complex examples for more advanced learners, etc. And this is something I can imagine potentially would be trainable, and people are probably working on this. I'm just not directly familiar with it. But yeah, so I can definitely imagine ways that potentially could be useful, creative ways that people could use automated systems like this that are doing a decent job with processing and producing and translating language to sort of complement the work being done by humans to try to optimize those teaching programs.
Yeah, I mean, I will say that as you get older, learning another language definitely gets harder. When you're young, it just sort of happens. Your mind is fundamentally more flexible to physically, literally more flexible to changing, and as you get older, that changes, and so does your ability to learn more languages. Of course, it's different for every person, and every person's going to learn differently. They're going to learn different paces. They're going to learn certain languages faster than they would other languages, right? It makes sense to them, but I can definitely envision that there would be some sort of startup somewhere right now that's using natural language processing to help you learn another language more quickly. I can imagine this would be something that would go in like a Duolingo kind of app. I mean, I can't imagine why they wouldn't. They already have lots of data, but I digress. That is a really interesting example, though, Anurag. Thanks for asking that question. All right, so now I'm going to ask you another, well, this isn't really a question that I want to ask you immediately, but there is so just one thing that I want to say quickly, actually, and that was that when we started the episode today, I was talking about how, it would be important for us to want to sort of maybe provide technology with this capability of being able to understand natural language so that humans can interact with language in a very similar way to how we interact with humans. And I was mentioning this a couple of episodes ago, but even, now, as I'm about to sleep and I tell Siri to set my alarm for the morning, it still feels just so incredibly natural to me to be able to think that I can talk to to an electronic device. Right? Fundamentally, my brain hasn't evolved in, for hundreds of thousands of years in a world where both humans and machines can talk. So my brain subconsciously is going, this is human interaction, right? This is being able to talk to another person, whereas consciously I know, no, this is just a bunch of math, right? Just because I have only ever associated language with intelligence doesn't mean you really need what we call intelligence to understand language. That's just the only way we've seen it done. It's always possible to be done mathematically too. But regardless of that, the sort of thing that I wanted to get across was, as I mentioned that, Akash made an interesting point on the chat, and that was that, if if coding was as easy as just talking to a computer, then I wouldn't want to do it, because then it sort of loses its value if everyone can do it. But my point is not that we're going to write code with language now. We're not going to be telling computers exactly what to do down to those little instructions with language, but rather the interfaces for end users are going to be powered by natural language, is my opinion, right? Like, you pick up your phone today, you open up Face ID, you use it, pretty intuitively. Fundamentally, there were programmers that had to write all of the instructions that go behind all of those applications, right? Coding isn't as intuitive as taking a note on your iPhone, because it was the programming that made the note taking that intuitive. Right, at the end of the day, the programmers are still going to be there writing all the code for that NLP, writing all the code for the applications that are powered by it. And who knows, maybe this NLP might help us generate code as well, right? We're seeing GPT-3, for example, can be used to generate code. Some people have said, oh, we're going to be replacing developers in the future, but I really don't agree, because if as a developer your only job is to take an exact description of what exactly needs to be coded for a front-end application and just implementing that, then, well, your days are numbered anyway, right? At the end of the day, your job as a developer is to implement logic. It's to come up with these creative ways of implementing systems, and then using the power of code to actually implement those systems that you've creatively designed. It really is an art, as you mentioned, Akash. It's not a science, right? I can't say I want to implement a chat app. This is exactly how I'm going to do it. I can't mathematically derive that system to figure out exactly what I want to implement, right? I've got to think. I've got to be creative. It's different every time. So the idea is that what I mentioned was that we want to make the experience for end users better with natural language, not that we want computers to be fully language understanding machines, right? So that's sort of the distinction that I wanted to make really quickly. Anything that you wanted to add to that, Allyson, around how NLP might be able to help us with code or with technology?
Yeah, no, I think that's a really important distinction that you made that I hadn't, thought of in terms of how people might interpret that comment. It's certainly the idea there is, we want to be able to program things, to engineer things, to be able to function in such a way that when users input language, those users will, be able to operate in a natural way. Certainly, there are some folks who have been working in interesting ways on sort of an interface between natural language and code, and working with models to work with code in addition to natural human language. Again, not a line of work that I am super directly familiar with, but absolutely, just as you said, sort of there's a tremendous amount of creativity and sort of continual thinking and development and creation that needs to be brought to bear when trying to design these types of models to work this way. So it's not the case. It's really, we're not even at a place where machines can necessarily just take natural language and translate it perfectly into a program. But even so, we aren't at a place where we can just perfectly articulate what that program needs to look like. So if we knew exactly what a perfect natural language understanding system needed to look like, then we could code it. Possibly we could write a program just to write that code for us in more or less trivial ways. But yeah, there's some real human creativity that has to go into the design of these natural language processing systems right now. So we're not in a place, as Tanmay said, we're not just saying, oh, we just want to be able to say, design me an NLP system that works perfectly, and that's not something that we're talking about doing as researchers or engineers.
Absolutely, right. It's all about augmenting those human capabilities, not replacing them. That's what it boils down to. Now, a couple more quick questions. Cecily is asking which libraries would I want to use when I'm doing natural language processing tasks. One that I will say really quickly off the top of my head: Hugging Face Transformers is a great one. There's an entire episode with the chief science officer of Hugging Face a little while ago that I will also link in the description below. But regardless, Allison, your answer for that question as well.
Yeah, I think for implementing machine learning models, I tend to point people toward PyTorch. I think that that's a useful one in general. Um, and and that I believe is what the Hugging Face Transformers library
Yeah.
uses. And so, yeah, PyTorch and TensorFlow both are examples of sort of libraries, platforms for implementing these types of models. When I have students coming to work with me, this tends to be, the basics as we're ramping up to work on this type of research. I tend to start them out with learning PyTorch. So that would probably be my go-to to point you toward.
Wonderful. Thank you very much. Also, something that you want to. I actually, right as I was about to say this, I see a comment from Sid about this. He's saying, I am stoked about Swift for TensorFlow, can't wait for further development. And you're absolutely right. Swift for TensorFlow and Flux are also two machine learning libraries that you should take a look at for natural language processing. Although I will say the level of support that the community has for like the thousands of people that are contributing to PyTorch, that's something that for a lot of production applications you can't really beat. But then again, there are some applications, actually a lot of applications, from all sorts of companies like Apple and NASA and so on and so forth, that really benefit from the computational advantages that you get when you use something like Flux or Swift or TensorFlow. So I would recommend taking a look at that. There are a couple more questions about more generally like some of the technical details behind like PyTorch and TensorFlow and what the advantages and disadvantages are. We're not going to cover that yet. We will be covering that in another episode very soon, which is going to be a very compiler-focused episode with a very special guest in the compiler world who has pioneered a lot of this tech. So I can't exactly tell you who it is just yet, but you'll stay tuned. It's going to be a very exciting episode. Now, last question today. This one's from Shiva. Can we use natural language processing technology to help people with disabilities that aren't able to fully speak or communicate?
Yeah, so this is a really great question. I think that it's going to depend on what types of ways that such users are able to interact with the technology. So if, for instance, you have someone who's not able to vocalize language, but is able to type, for instance, and formulate sentences, then this is a way that certainly that user could interact via text with an NLP system. If you have a user who, for instance, might suffer from aphasia and may not even in writing be able to formulate language that they would like to use to express themselves, then this is going to be a more difficult thing for those natural language processing systems. Certainly systems trained on sort of standard data within the training distribution. It's going to be harder for those models to work with that type of language. There's going to be a lot of variety in terms of the sort of language that you might see. But I can certainly imagine this would be a great type of research topic. Likely there are people who are working on this type of thing as well. Sort of if we can see regularities in the types of outputs that such users are producing and train models to be able to accommodate that type of language in addition to the types of language that we see from other users, that would be really great if we could sort of find ways to decode potentially atypical language inputs. Other types of instances, let's see, there's some really interesting work being done with brain-machine interfaces to try to sort of circumvent the output interface and instead be able to read brain activity directly and try to train models to be able to decode that to be able to operate in useful ways. That's a really cool line of work. I do not know very much about that line of work, but it's a neat type of thing that could potentially be used for this type of instance. And also an interesting area is in trying to be able to use natural language processing not only on text, not only on spoken language, but also on signed languages, which of course is more of a visual medium and requires being able to decode those signs from video. And so this is an interesting line of work as well, but certainly one that's very worthwhile, given that obviously we have human users who are also communicating in signed languages. So yeah, a wide variety of different ways. It's a great question, and I think something that deserves continuing development in these lines of research.
Wonderful. Thank you very much for sharing. That's I can't wait really to see how NLP could help us, figure out how to provide these communication abilities to people who don't necessarily have a full communication ability because of those disabilities. I think that's one of the sort of really impactful applications of this tech. This is something that I've actually worked on in the past and continue to sort of work on, where I feel like the bottleneck currently isn't even the NLP technology, it's more of even hardware, right? Like for example, what you mentioned around brain-computer interfaces. Some of the biggest challenges are how can we get enough output from the brain with enough density to be able to actually understand that data, right? That's the challenge at the end of the day. But that was a really interesting discussion. I mean, I've personally learned a lot from you, so thank you very much for actually coming on the show. I really appreciate it, and I'm sure the audience has learned a lot as well. Now, I mean, of course, if there are any questions that we couldn't get to or that I missed, feel free to put those in the comments, and Allyson and I will get back to you as well. But I will say now that before you leave today, I wanted to ask you: is there a closing message that you want to share with the audience? Something that you're passionate about, something that you think you want to share with everybody in the audience today?
Sure, yeah. Let's see. So I think a message that I like to convey to folks along these lines is that right now we're in this interesting place in the field of NLP where we're getting some really impressive looking outputs from these models. We are seeing a lot of legitimate advances, but we're reaching a place where it's harder and harder to try to disentangle what is real human-like robust language behavior versus things that are just really powerful statistical engines that are very good at sort of mimicking the types of language and outputs and completions that are the types of things that these models are trained to do. So I think it's just worth keeping in mind as someone who's interested in NLP and artificial intelligence that there are a lot of challenges in evaluating these models and in trying to define exactly what it would mean to really have achieved something like understanding, something that's really human-like. And this is also a very important part of the field. And so as you see these advances coming out, I think it's important from a lot of different perspectives to take the results with a bit of a grain of salt and wait and be thinking about sort of like what is it that would count as true natural language understanding? What is it that would count as a system that I would be comfortable with trusting with important decisions? We don't want to be deploying these systems in ways that are dangerous and risky if we don't really know how strong they are. And so these are the types of things it's important for us to get a strong handle on exactly how these models are working, what their capacities are, where they diverge from actual human intelligence, so that we can know where we can safely deploy them and also just assess in general what the state of the field is.
Thank you very much, Allyson. I really appreciate it. That's such a thoughtful closing message. We've learned so much today. I mean, all the way from how language models and Tetris bots and police departments, everything at the end of the day is based off of the objective that you define, right? That is the key. Without the proper objective, nothing is really going to work. You always need that, right? All the way down to why language models learn the way they do and what some of these sort of new cutting edge solutions are that we're working on. I really appreciate you coming on the show. Before we end today, I feel like we might as well end on a fun note, thanks to Sid on the live chat. He gave us an NLP joke, one that you've probably heard before. Allyson, he says, an MIT linguistics professor was lecturing his class, and he says that in English, a double negative forms a positive, but in some languages like Russian, a double negative remains a negative, but there isn't a single language in which a double positive can express a negative, and a voice from the back of the room piped up, yeah, right. So that was nice. I mean, I feel like that's an example of sarcasm. I can't wait for the day that language models can understand that too. But that was really interesting. Thank you very much, Allyson. Really appreciate you coming on the show today.
Thank you as well.
Thank you. And I also want to say a huge thank you to everybody joining the live stream today. I really appreciate you joining in as well. Remember, this series is held every Sunday in the morning Eastern time, so make sure you join us next week. We've got some really exciting stuff lined up, and I cannot wait for you to see it. In fact, the next few episodes are going to be really, really fun, so make sure you join, and I will see you in the next episode. Thank you, Allyson. Thank you, everyone, for joining in today, and goodbye, everybody.